In this video, we're going to do some extra examples computing antiderivatives or indefinite integrals. So let's start with this first one here. So we have the indefinite integral of 3 times the fourth root of x cubed, with x as our variable. So I'm going to begin by rewriting this. So first of all, I can pull the 3 out of the integral, okay, and I can also write the x. Instead of the fourth root of x cubed, it's actually x to the 3/4. Okay, and then I can use the reverse power rule. So this is going to be 3 times, so if I add 1 to the exponent, I'm going to get, so I want to add 4, I'm going to have 7/4. And then maybe I'll just do this over here. If I do 1 over that number, okay, this is actually 1 times the flip of that number, so it's 4/7. Okay, so whenever you're doing this with a fraction in your exponent, the constant out front is always the flip of your fraction. Okay, and then I have my plus c. And then if I just simplify this, it's going to be 12/7 x to the 7/4 plus c. Okay, so that would be my indefinite integral here, or all antiderivatives of this function. And again, you could take the derivative of that to make sure that it matches your integrand. So if I took the derivative of this part, the c derivative is always 0. I should get what is in what's my integrand, so the thing inside the integral. Okay, let's try another one. So I want the indefinite integral of 3 over 2x to the 5. So again, I want to rewrite this. I'm going to do this in a couple of steps because people often get confused here. But I could think about this as 3 over 2 times 1 over x to the 5. Okay, so that 5, the fifth power, is only on the x. It's not on the 2. So when I bring it up as a negative, the 2 is going to stay on the bottom. Okay, so it's 3 over 2 times x to the negative 5. Okay, and then I can bring the 3 over 2 out of the integral because it's a constant, and I have just x to the minus 5 dx. And now I can take my integral using the power rule again. So if I add 1 to the exponent, it's going to become negative 4, so I need to divide by that number to make sure that when I take the derivative, it cancels out. So simplifying, this is going to give me negative 3/8 x to the negative 4 plus c. And I don't really like negative exponents, so I'm just going to drop that to the bottom. So it's going to be negative 3/8 x to the 4, so positive 4 plus c. Okay, so that is my indefinite integral here. And again, remember, you can always check your answers by taking the derivative. Okay, now a slightly more complicated one. So here I have the indefinite integral of x minus 4 over root x. So for this one, it looks kind of complicated. I don't know how to approach it. I don't know what the antiderivative of this function is. So what I want to do is simplify. Okay, now there's a couple of ways I could simplify this, and it seems like students either prefer one or the other. So I'm going to tell you both. So the way that I prefer, actually, is to split this fraction. So maybe I'll just do the simplifying twice. So actually, I'm going to not do it. I'm going to do it in a different color. So let's do the first one in blue, sorry. So what I'm going to do is when I have a fraction with addition or subtraction on the top, I can split it into 2 fractions with the same denominator. Okay, so I could actually rewrite this as x over root x minus 4 over root x. Okay, now I can simplify each of these. Okay, so x over root x, this is x to the 1 over x to the 1/2. So if I subtract those exponents, I get x to the 1/2. And then over here, I'm going to have 4 times x to the minus 1/2. So then we could split it up but actually I'm just going to stop there. Or, okay, we could have, instead of making this, if we didn't notice that this fraction, we could split up the fraction. So another thing that people like to do is to put the top and then multiply by x to the minus 1/2. Okay, so we could just bring that root x to the top by making it a negative exponent, and then we can expand it through to the brackets. So then we're going to get x to the 1 times x to the negative 1/2. Okay, so that's actually x to the positive 1/2 when I add those exponents. And then I have minus 4x to the minus 1/2. Okay, and now notice that these are the same. Okay, so whichever way you do it, doesn't matter. They're doing the same thing. Some people prefer the fraction. Some people prefer to bring it up to the negative exponent and then expand. Okay, either way, they both work. So now that we have this integral, so I'm going to keep going in my normal color, I'm going to split it up so I can do these separately. So it's x to the 1/2 minus, and I'm going to pull out the 4, x to the minus 1/2. So I can do these parts separately. So when I add 1 to the exponent here, I get x to the 3/2, which means I need a 2/3 out front, the flip of the exponent. Okay, now for the second one, when I add 1, it's going to be to the 1/2. So my constant out front is going to be 2/1, or to the 2 times 2. And then plus my constant, because I have evaluated the antiderivative now, or the integral. And then if I just rewrite this is 2/3 x to the 3/2 minus 8 x to the 1/2, okay, plus c. So this would be my family of antiderivatives. Okay, let's try some more. Here we have some exponentials and some trig functions. So when I'm doing an exponential integral, so I'm going to begin by pulling out that 3. Okay, so I just have the exponential pi t dt. So when it's a constant, so you could actually, now that we've seen substitution, you could use substitution here, but you don't have to. So when it's a constant, we normally think that it's going to come, so when we take the derivative of an exponential, we always get the exponential back. So I might think that my integral, my antiderivative is e to the pi t. If I differentiate that, I get e to the pi t times pi, the derivative of the exponent. Okay, pi is just a constant, so I could just add in a 1/pi, and then I would have a 1/pi here, and the pi's would cancel, and then I would get my integrand. So that's my antiderivative, or that's an antiderivative. So it's going to be 3 times 1/pi e to the pi t plus c. So we get 3/pi e to the pi t plus c. And again, like usual, you can take the derivative and make sure that you have the right answer. Okay, so trig 1. So I want the indefinite integral of 2 sine theta plus cosine of 5 theta d theta. So the first thing I want to do is break this up. So we can bring out the 2, and then I have the integral of sine theta d theta plus the indefinite integral of cos of 5 theta d theta. So first of all, I want to know what has derivative sine theta. Okay, and I know the derivative of cosine theta is negative sine theta. So that means that this integral is going to be negative cosine theta. Okay, now when I do this one, I want to know what has derivative cos of theta, and that's sine theta. So if I want cosine of 5 theta, it's going to be sine of 5 theta, except that I'm going to get an extra factor of 5 there. So what I'm going to do is multiply this by 5/5. Okay, so I'm multiplying by 1. So I'm just doing this a little bit differently than we did the last one, so you can see. So then we can bring this 5 in, okay, into our integral. So I'm going to have negative 2 cosine theta plus 1/5 5 cosine of 5 theta. Okay, and the thing that has derivative 5 cosine of 5 theta is actually sine of 5 theta. So then I'm going to get minus 2 cosine theta plus 1/5 sine of 5 theta. And now I have my constant of integration. Okay, now you could do this the same way we did the E one, so you could guess that it's sine of 5 theta, and then realize you need to add the 1/5 to get rid of that extra 5 you get when you use the chain rule. Either way, okay, it doesn't matter. I just wanted to do it a bit different here, so you can see all the different methods you can use. Okay, so one more until we get into a word problem. So I want the indefinite integral of 1 plus 3x minus 5 secant squared x dx. So again, I'm going to split this up. So it's 1, the indefinite integral of 1 plus 3 times the indefinite integral of x dx minus 5, the indefinite integral of secant squared x dx. Okay, so what has derivative 1? Okay, well that's just x. Okay, this is like x to the 0. Okay, so you could also think about this as x to the 0. And then you can use the power rule. So if I add 1 to 0, I get x to the 1. And then I times by 1/1. Okay, so I just get x. Plus 3. And then I'm going to use the power rule here. So it was x to the 1. So it's going to be x to the 2, which means I need a 1/2 out front. Now I want to know what has derivative secant squared x. Okay, now I know that this is tan of x. The derivative of tan of x is secant squared. So that's going to be minus 5 tan x, and then I have my plus constant. So then if I just rewrite this, it's going to be x plus 3/2 x squared minus 5 tan of x plus our constant of integration. Okay, so that is my infinite family of antiderivatives here. Okay, let's try another one. So, suppose an object is dropped from a height of 144 feet with an initial velocity of 0 feet per second. So they also give us this note here. The acceleration of a dropped object, if you ignore air resistance, is a constant. And it's approximately 32 feet per second. And I think if you're using meters, it's 9.8 meters per second, something like that. But we're going to use feet here because they gave us everything in feet. So we'll use that. So we want the equation giving the position of the object at any time. Okay, so I'm going to call that S of t. So S of t is going to be the height of the object at time t. Okay, now what we were given, okay, so we know that when we before we drop it, the height of the building is 144 feet. So the object at time 0 has to be 144. So I know that S of 0 is 144. Okay, so at time equals 0, the height is 144 feet. So that's just before we drop it. And then we want to remember that when we have a function that gives us position, okay, so when our function S of t is position, then when I take the derivative of that, we sometimes call that v of t because it gives the velocity of the object. And when I take the derivative of that, or the second derivative of s, we sometimes call this a of t because it's giving us the acceleration. Of the object. Okay, so with that in mind, we also know, so the velocity, when we first drop it, so that's v of 0, okay, is 0. So we know the velocity. Okay, so initial velocity, so that's at time 0, is 0 feet per second. Okay, and we also know they gave us this acceleration. Okay, so we know that a of any, actually a of t, for all t, is 32, but because the object is, so the velocity, because we're height is decreasing, the velocity is going to be negative, but the object's going to be speeding up, so the acceleration is also negative. Okay, so it's going to be negative 32. And that's for all t, because it's constant. So if we want, so now we know the acceleration, okay, function. So we want to go backwards to try and find the position. Okay, so that means that v of t, okay, is going to be the antiderivative of the acceleration. And t is our variable here. Okay, so that's going to be negative 32t plus our constant. Okay, but we know that v of 0 equals 0. So that means if I plug in t equals 0, I should get a velocity of 0. Okay, and this is going to tell me that c is actually 0. Okay, so now I know that the velocity, v of t, is actually just negative 32t. Okay, so this is useful. So we found the c value there. So now when we want s, and I'm running out of room here, we want to integrate, because v is the derivative of s, we want the integral of v of t with respect to t. So we want to take the integral of negative 32t dt. So I can pull out the negative 32, so it's t dt. And I know that this is going to come from a t squared, and I need a 1/2 there, and then plus my constant. So that means that s of t, is going to be negative 16 t squared plus c. But again, I have an initial condition, so s of 0 is 144. So that means 144 is equal to negative 16 times 0 squared plus c. Okay, so this part is 0. So that means that c is 144. So now we have our formula for the height. So s of t is going to be negative 16t squared plus 144. And this is the formula that we were looking for. So that is going to give us the height at any time t of this object. And now we could ask things about the object. For instance, how long does it take to hit the ground? And what's its velocity when it impacts? Okay, so if we want to know when it hits the ground, okay, so this is when the height, s of t, is equal to 0. Okay, so that means that we want t so that s of t is equal to 0. Okay, so that's going to be negative 16t squared plus 144 equals 0. I could factor out negative 16, and then I'm going to have t squared minus 9. So then if that's a difference of squares, so I can have it t minus 3 times t plus 3, which means that I get t equals 3 or t equals negative 3. So I seem like I get two answers, although negative time does not make sense. Okay, so it doesn't make sense in terms of the problem. So that means that it's not in the domain. Okay, so that means that object hits the ground after 3 seconds. Okay, because we had t equals 3 here. And its velocity then is v of 3. And v was negative 32 times t. So negative 32 times 3, which is negative 96. And the units are feet per second. So that's going to be its velocity when it hits. So that was some examples using indefinite integrals and also initial value problems. Okay, so here we had where we knew some sort of initial conditions. Okay, so this is the height, the initial height, and we also knew the initial velocity. So these two things enable us to determine the c after integration, so the constant of integration. So if we didn't have these values, then we'd have some constants that we didn't know. But because we have those values, we're able to determine those constants.